Okay, I propose that we start. Welcome, everyone. Welcome to this seminar in Ecology and Evolution from Montpellier. So I remind those of you who are online that you are in a webinar mode, which means that your mics and cameras are automatically switched off. If you want to ask questions to today's speaker, please use the Q&A tab, and we will allow you to start your mic and camera to ask your questions. Otherwise, if you have technical issues, you can report in the chat. And before giving the floor to Olivier to introduce our speaker, I remind you that there is an ongoing call for next speakers, so you can invite people. So do not hesitate to submit your proposals by what's the final dates, Céline? When should we submit? You don't remember?
Okay. End of November, beginning of mid-December.
Okay, but yeah, you can submit your proposals, and we have some problems, so we'll try to solve this before we start really. Where is mute? Do we hear anything? Yeah. Sorry for the delay, we have a technical problem. Ouais. Un, deux, un, deux. Alors, je propose qu'on commence comme ça. On a un petit écho, je ne sais pas. C'est bien, non? Ben ouais, on ne sait pas ce qu'on va faire. J'arrive pas de son de la délire.
Yeah.
Ouais, là, je pense qu'on a validé. Ah, ok, c'est bon. Eh ben, à toi la parole.
Good morning, everyone. So it's my pleasure to welcome Christie Le Coeur today. So, well, I'm Olivier Giones, sorry. And Christie is doing a 1 year lecturer position at the University of Montpellier. It's an ATER position. And we're very lucky to have her at CEF with us. So she's based at CEF. If you want to meet with her, she's not very far from here. And Christie did a PhD at the museum in Paris. And then she left for postdocs in Norway and Finland. And now she's back in France, and we're very lucky to have her in Montpellier. And she's working on the influence of environmental variation on population responses. And to do that, she's using the demography, and that's exactly what she's going to talk to you about today. So I'm just give the floor to you and Spanish.
Thanks, Olivier. Thanks also for giving me this opportunity to present my work today in this seminar. And in particular, today I'd like to introduce and to present some of the research questions and research projects I've been working on during my postdocs, since my postdocs actually, where using different approaches, I try to better understand how population can respond, like wild population of animals, plants, can respond to changes in the conditions, environmental conditions, and in particular the variability in these conditions, in particular under climate change. So I'm pretty sure that you're all familiar with, maybe with the maps. Yeah. With this kind of figure, or at least the main message, showing that there's a trend in the temperature, annual temperature, over time. So here is an illustration in France, but it's something that we observe, it's a pattern that we observe across the globe. And basically, since the 19th century, temperature has risen, and with a speed, like a speed rate increasing for the most recent years. And we know from many different studies that such changes in the trend, in the mean conditions, have strongly impacted all the different organisms from individuals to ecosystems. And at the population and species levels, we know that a change in this trend have induced some shifts in species ranges, in their phenology, in their physiology as well, with the consequences to have less or changes, at least, in the abundance and the distribution of many species at the local and global scale. But such changes in the mean conditions is one component of climate change, and it actually occurs concurrently with over at least two types of components that you're probably also pretty familiar with. The second one is a higher frequency of extreme events. When we think about extreme events, we mean like a higher number of droughts or flood events, more wildfires, as illustrated here in San Francisco or Australia in 2020. And such increase in the frequency of extreme events is, again, a common pattern that we observed on land, but also we saw some evidence on the marine environment. It's again very global. Such changes in the extreme events can obviously impact also in the same time the change in the mean, the distribution and the abundance of species. And the third component, which is actually the component that I'm focusing on, is a change in the short-term temporal variability. So what we expect, and what is already observed in some areas, is an increase of this short-term temporal variation on the short term, but like on a short scale, I mean. And I'm interesting, and that's what motivated my work here, is like to see if this component is actually an important component when we try to understand how population like persists or can survive with all the changes related to the climate change. So when we'd like to study this question, we'd like to understand how a change, or at least some fluctuation in the environment, can impact the stability and the persistence of a population. To measure the persistence of a population, we can, for instance, use in demography the long-term population growth rate. This matrix indicates if a population is expected to grow, to decline, or to remain stable over time on the long term. So it's a good index of fitness. But to understand the relationship between the two, like if we have a positive relationship or negative relationship, we have to dive into the demographic parameters. Demographic parameters are, for instance, the survival rate, fertility coefficients, or the growth rate in the population. Here I illustrated for a fictive population, 3 different demographic parameters, survival of juveniles, subadults, and adults in the population, but can fluctuate, and here fluctuate in the same time as the fluctuation of the environment in terms of precipitation and temperature occurs. And such variation induce variation in the annual population growth rate, so like the fluctuation in the abundance from one year to the next, which can influence then the long-term population growth rate. Based on theory, but also on empirical evidence, we expect that an increase of environmental variability would increase the variance of the demographic parameters and then increase the fluctuation, so less stable population, which decrease the long-term population growth rate. So we expect negative effects of such increase in the environment. You have like the equation, just a mathematical explanation of what I've just said, where if we have here the population growth rate in a mean environment, we can see in that equation that everything that can increase the variance of annual population growth rates will reduce the long-term population growth rate. But we also know that most of the population and species have evolved in varying environments, like they live in varying environments for years. Maybe not as much as we can expect with climate change, but at least some variation. So such fluctuation in the abiotic and biotic conditions have probably selected for some adaptation to the species and populations and individuals to live in these varying environments. And there are some assumptions about potential adaptation to such variation. One of them is the demographic buffering. Just to reduce negative effect of environmental variability, natural selection should favor some reduction in the variation of some important demographic parameters, so that it decreases the potential negative on the long-term population growth rate. So here, if I talk about buffering, I mean that you have still some fluctuation, but less variation for some demographic parameters compared to others, where here they can vary more freely than the other ones. And under the demographic buffering hypothesis, we expect that the most influential vital rates or demographic parameters, when I mean most influential, it means one that if you have a small variation, then you have big impact on the long-term population growth rate. So you expect that these rates, the most influential, to be more buffered against the variation in the environment than other rates. Using like another background on the life history theory, we also expect that these most influential vital rates, demographic parameters, will change according to the life histories we consider. So if, for instance, we have a population along this fast slow continuum of life histories located at the faster end of the continuum, meaning that it's species that most of the time have a low fast generation time, a short lifespan, high fertilities, and we have basically the opposite patterns for the slow living species, we will get different prediction on the most influential vital rates. So for the faster living species, we expect, for instance, that survival of juveniles or the fertility rates are the ones that should be buffered under the demographic buffering hypothesis. But interestingly, we also know from theory and evidence, empirical evidence, that positive effects can also be observed. And that's a question I was particularly interested in, just trying to understand why and what conditions are required to observe such positive effects. In a different research project, I tried to answer 2 different questions. The first one is just related to this relationship between variability, observed climatic variability, and the long-term population growth rate based on empirical data, and trying to see if we can see some relationships, and if we see some common patterns among different species, among organismal groups. And on second point, on second project, I was focusing on this positive effect and trying to understand in the context of climate change, which species or which population can actually benefit from an increase of variability in their environments. So if I start with the first question, to answer that, I gathered long-term abundance time series across the Northern Hemisphere, where I use very selective criteria, very strong selective criteria to get like good quality data. And one of the main parameters was very long-term time series, where at least 20 consecutive years of abundance were recorded. And at the end, using different sources like the Living Planet database or some literature search as well, we got 59 wild population for which we had at least 20 consecutive years of abundance records. And this population represents 5 different organismal groups: amphibians, reptiles, herbaceous plants, mammals, and insects. Basically, for each population, we have then a time series of abundance for which we estimated the annual population growth rate. So if we have 20 abundance records, we have 19 annual population growth rates. And based on that, we use 2 metrics, population metrics. The first one is an index of how much population vary depending on the observed climatic variability. It's the coefficient of variation of this annual population growth rate. The second one is the measure of the long-term population growth rate. So here we use the absolute values of this long-term population growth rate because we have no expectation of a direction of the relationship for all these organisms and all different populations across the Northern Hemispheres. It could be positive and negative, and we cannot make some strong expectation on that. So we use just the absolute values as an index of the magnitude of the response. And then for each population, we also collected data on temperature and precipitation to quantify the variation in the environment in terms of climatic conditions. So we estimated the standard deviation of temperature and the coefficient of variation of precipitation for 2 seasons: the growing season, the active seasons, and the inactive season, which is basically the fall-winter season. And then we tried to see if we have some relationship between the 2 different population metrics and this variation in the climatic conditions. Using the background that I previously introduced, we made 3 predictions. If we detect some relationship, we expect a positive relationship between more variation in the climatic conditions and more fluctuation of the annual population growth rate, so less stability for the population. A positive relationship, again, between here, the climatic variability and the absolute value of the long-term population growth rate. So they respond more if you have more variation in the climatic conditions. And if one of the 2 relationship is detected, we expected more or stronger responses among the shorter-lived species. So we use here longevity as a proxy of the fast-slow continuum of life histories. So if I start with the first prediction, we did find some relationship, positive relationship, between the coefficient of variation of the annual population growth rate and the temperature, variation in temperature during the active season only. And this is common, like the common pattern that we observe for all organism groups. And we also detected some relationship with the coefficient of precipitation, coefficient of variation of the precipitation in the active season again, like nothing was detected for the inactive seasons, but the relationships differ depending on the organismal groups considered, and most of the relationships are pretty weak, so that was partly expected. So we see here that for herbaceous plants, for instance, or reptiles, we have a slight positive relationship where if you have more variation in terms of rainfall, you have more variation of the annual population growth rate. We see that insects and mammals were less responsive, and we have the opposite counterintuitive results for the amphibians, where a negative relationship was observed. When I looked at the long-term population growth rate, we detected some positive relationship, but very small again. And most of the time is like no response for the other organismal groups, regardless of the seasons considered, meaning that the relationship is pretty weak again. And we have, in that case, no negative relationship, or only positive, or no like flat relationship between the two. And for the two different predictions, where we expected greater responses for the fast or shorter-lived species, we actually didn't detect that. We did find that all the species that have short lifespan or intermediate lifespan fluctuates more, have like a higher long-term population growth rate variation, but we cannot link that to the observed climatic variability. So if I just summarize that, we detected some positive relationship, but also some negative for at least amphibians. So weak relationship overall between the observed climatic variability and the population persistence and lability, which was one of our prediction at the beginning. When you compare so many different populations with different locations, you know that many other parameters, but even if we control as much as possible to other factors who can influence their long-term population growth rate, you know that you don't measure everything. And that can counteract, for instance, an effect of observed climatic variability. Such variability can impact, of course, directly, but also indirectly, the populations. And ideally, it would be very cool to have data on different populations for the different locations, but it's really almost impossible. At least I cannot find such data because you need very long-term time series to be able to test that. We see that there's an importance of the time scale. Here, I didn't really present that, but we use different time scale to quantify the variation of the populations and the climatic conditions. And then, like, it's also important, like if you have like a very short, like 4 years or 8 years, you have stronger responses at the 4-year scale than the 8-year scale. The season is also important, and of course, the organismal groups considered. But one of the main conclusions here is that potentially like the response to observed climatic variability is probably population specific, where you have to consider that other important parameters can be or counteract what we observe on the observed climatic variability. And you should, for that, be able to understand how the demographic parameters respond and not only the abundance. So that's kind of the second part for the second project, where I focus on what explains from a demographic background or theory, like the variation in the annual population growth rate. And as I said, I focus on these specific questions, like can some populations benefit from an increased variance in their environment? Could we detect that, and what would be the conditions for that? So if I go back on this figure again, the negative effects of increased environmental variability on the long-term population growth rate is negative in a case where we assume that it increases the variance of the demographic parameters, but doesn't impact at all the mean or the average values of the demographic parameters, and then the mean of the annual population growth rate. So the underlying assumption here is that the relationship between the demographic parameters and the main drivers of this variation is actually linear. So if we look, for instance, here, like if it's the mean of the demographic parameters, then you have fluctuation in the environment around this mean. You will increase the variance, but the mean will remain the same. So that's one of the strong assumptions behind the mathematical developments, but also on the expectation we make. So what now? What if actually the demographic parameters respond differently to the environmental variability with like some nonlinear relationships, some linear relationship, like a complex structure? Here you have, for instance, 4 different cycle rates for a population, fertility rates. We have like a kind of a logistic relationship survival rates of stage 1 and stage 2 will also fluctuate from a nonlinear relationship, and the stage 3, which is mostly linear and at least buffered against any variation in the environment. Such ideas that the nonlinearity can impact the long-term population growth rate is because such changes in the relationship will change the mean of these demographic parameters. If we have convex relationships, we expect that such relationship will increase the mean of the demographic parameters due to the density inequality. But if you just look as an illustration here with the annual population growth rate, if you have the long-term population growth rate in a constant environment, if you now have like variation around this mean environment, and you estimated again the long-term population growth rate, you will have, due to this convexity, an increase of the long-term population growth rate. So such ideas that the relationship can be nonlinear or a mix of nonlinear and linear relationships between the demographic parameters and the main environmental drivers makes a new assumption, a new hypothesis, that actually lability, like the fact that some demographic parameters can vary a lot, could be an adaptive response, an adaptive demographic response to variability in the environment. I don't know what is in the music from now. And then such lability can be adaptive in the only case where you have an overall increase in the mean of the demographic parameters due to some convexity. That's what I wanted to try, to understand if it's possible to observe such convexity, and if we can actually detect some long-term population growth rate that is positive, so a positive effect of an increase of variability. So to answer this question, I first start to extend the two-J-Le Coeur's approximation to include a new component in this equation that reflects how much nonlinearity we have among all the demographic parameters in a population. So if we have here the demographic parameters against main environmental drivers, let's say temperature, we have what I call 0, like the mean demographic parameters in the mean environment. And we can actually quantify whether the relationship with the environment around this mean is convex, concave, or linear. And the nonlinearity component is strongly related to what we call a nonlinearity index, which gives an information of the overall convexity or concavity in a population. So we consider all the relationships with all the different parameters, and we weighted that by the importance of one of the demographic parameters for the long-term population growth rate. So we have this nonlinearity component, and we still have the variance-covariance component that is already developed on the first equation. So the nonlinearity component can be positive if most of the data rates, most of the demographic parameters are convex. It could be equal to 0 if it's linear, and we will get the same equation as the first one, or concave if most of the demographic parameters show concave relationships. The variance-covariance components could be equal to 0 when most of the demographic parameters are actually buffered against environmental variability, or negative if it's vary a lot, or if the relationship between the different demographic parameters are positive, so they covariate positively. So from this equation, we understand that the only option to observe a benefit on the long-term population growth rate of an increase of the environmental variability is to observe higher nonlinearity components against, like, compared to the variance-covariance components, meaning that you have a better increase in the mean of the demographic parameters which can outweigh the negative effects of an increase in the variance of these demographic parameters. So we used this equation, and we used like a simulation framework to test this. and see across generation time, across different populations, if we can detect such positive effects. So to start with, we used 154 matrix populations models from the Ecology open access database. So matrix population models is simply a matrix who gather all the mean demographic parameters for a population. So here is just a population with 3 stages where we have the mean fertility and the mean survival for the different stages. And we use these values for the 154 populations as the mean demographic parameters for the mean environment. So that's the start. And from that, we simulated some environmental stochasticity. So we created like an environmental variable, and we created some simulation of its variation around this mean environment and this mean demographic parameters. And we use 13 different scenarios where we use different link functions. So we use different type of relationship and different covariance between the demographic parameters, positive or negative. But one important aspect that we have to understand here is that we didn't define if it's convex or concave. Like the curvature is defined by the mean values of the demographic parameters. So here we apply exactly the same scenarios to all demographic parameters, but the shape, like the curvature and the variance of each of the demographic parameters varied depending on the mean values. So here you have, for instance, mean survival, 3 different values, and then 3 different shapes according to that. So we did that for all populations, and then from that, we quantify the long-term population growth rate, the nonlinearity component, and the variance covariance components to try to understand what happened. I won't show here like all the results from the 13 scenarios, but the key results. One of the scenarios we've tried is what we call a forced buffering scenario, where we forced survival of mature individuals, so the one we can reproduce in the populations, to be completely buffered against any variation in the environment. And we allowed survival of immature stages and the fertility rates to vary freely along a nonlinear relationship. Again, here is an illustration, like the shape curvature will change each time for the different mean demographic parameters and for each population. Here, survival of the immature stages and fertility rates could vary negative, as you can see, if one increase, the other decrease. From that, we quantify for each population the long-term population growth rate. And on this plot, if you see like one black dot, it corresponds to one population, so one estimation of the long-term population growth rate for this population that have a specific generation time. So like it's about 107, I think, different species that is represented. And we have like, if the black dot is close to the dashed line, it means that the simulating some variability in the climatic conditions didn't really impact the long-term population growth rate. So the population is pretty much buffered to such variation. If we have here more like negative values, it means it has a negative effect on the long-term growth rate, and the opposite for the upper part of the figure. So if I show the results, we have here like 154 different estimations across generation time. And where we can see, if we look at the generation time after 20 years, let's say, it's pretty much buffered. So like regarding of who can actually fluctuate with the environment, the long-term population growth rate is equal close to 0. So it means that it remains stable. But if we go to the faster, like short-lived species, we can see that actually the long-term population growth rate can be positive in that case. And if we try to understand why, we can just decompose this long-term population growth rate into the nonlinearity components for fertility rates, survival rates, and the variance covariance components. So if we go slowly on that, you have on the y-axis the contribution to the long-term population growth rate, of the non-linearity in fertility in red or in yellow on survival, and the effect of variance covariance of these demographic parameters. So if we look at the red points, red dots, we see that for the fast-living species, you have some convexity on the fertility rates that is happening for the very fast-living species. If we looked at the non-linearity in the survival of immature stages, you have higher, like stronger convexity observed, which makes at the end positive effects of the convexity. And when we looked, when we compare like this non-linearity effects with the variance covariance effects, we see that actually the global non-linearity components can outweigh the negative effect of the variance of these demographic rates. Interestingly, if we do exactly the same scenario, but now we change how the survival of immature and fertility rates can covary, they now covary positively with a change in the environment, we get the opposite patterns. So it means that here we have negative effects on the long-term population growth rates, while we get like a positive effects before in the first scenarios. And this can be explained by the change in the variance covariance components. Like having positive covariation between the demographic parameters, it means that if you have a change in the environment, it changes both the survival of immature stages and the fertility rates. It increases how the population responds to such changes and has a stronger negative effects. And then even if we have the same convexity in the population, in the way they respond to environmental variability, this cannot compensate the negative effects of such increases. So from these scenarios and all scenarios, we made some conclusions, but if we detect some positive effects, it would be only among the faster living species. And that population with the short and intermediate generation time are the ones that are the most responsive, positively and negatively. Like sometimes we have very strong negative effects because the variance covariance is pretty high, and this is always observed among the faster living species, which also means that the longer lived species is pretty much preferred against some changes. If we detect positive effects, it means that we have a positive linearity component due to convexity that is associated with a reduced variance covariance component due to negative covariation. And the main conclusion of this work is that if we detect like the species that have the largest, at least potential for using the adaptive demographic ability are the fast-living species. Among the long-lived species, demographic buffering seems to be one of the main adaptive demographic response. Positive non-linearity components have been observed in some scenarios, but very slight positive effects, which cannot actually lead to positive effects. So the next step for me would be just to test whether we can observe such non-linearities. We have evidence that non-linearities in the demographic parameters response exists in the wild, but this again requires like very precise and detailed demographic analysis and data sets. And I would like to try whether we can actually see some benefits of the environmental variability in the wild. That would be the next step. I think I'm done. I would just like to thank, of course, the collaborators, nice collaborators for the studies. So I did the first one at the University of Turku in Finland, and the second one at the University of Oslo in Norway. And I'd like, of course, to thank you all for coming in the room or online as well. And I'd be more than happy to answer any of your questions if you have.
Parce que je vais couper le son ici et je l'allume de l'autre côté.
I wanted to come back to the fact that do we really have evidence, and do you see that in your data, that the variance around the warming trend of climate variable is actually increasing or not? Because it's not the trivial. When sometimes predictions say that actually it's not increasing, it's just like we're hitting the roof more often.
Yeah.
But and so compared to what the consequences of what you're exploring, I mean, do we have evidence that actually climate variability around that trend is increasing or not in those data?
So does it work? Not really. It works? Okay. It works. That's a very good point. Is like from the first introduced and presented here, it's something that I was looking at, like whether actually we can detect some higher fluctuation.
You kind of mentioned it, I think, for a bit for the first question. What difference would it make if you started playing with like the time frame over which your environmental variation started happening over like shorter or longer time frame? Because I imagine, especially with the kind of fast flow continuum thing, then you end up with species that are spectrum experiencing the variation. Whether those kind of different bits. I think you hinted at maybe, but
yeah. Yeah, it's like at the starting of this study, for instance, we just were thinking about how to quantify this variation. Should we look at daily variation among the seasons? Or we looked at monthly variation, annual variation? So there's plenty of possibilities. And again, it changed according to the biology of the organisms we studied. For instance, when we observe the positive effects of the long-term growth rate, like the absolute value of the long-term growth rate for insects against variation in the environment, we're thinking that looking at the 8-year time windows doesn't really make sense for such species because it's so a short time generation time. But you don't expect that variation on the long term could influence that much such organisms. So that's why we use both, because we were thinking that for the long-lived species, 8-year variation can have direct or lagged effect on the demographic and population dynamics of such species. So we looked both of them, but not like with some different prediction or expectations for them. But on average, for the 8 years time windows, we detected sometimes positive effects, but it's always with less like the slope was always a bit slower, like not slower, but lighter.
My question is very related to your answer to Matt's question and Matt's question.
since I noticed that you chose your species, the 59. By the way, there's no birds. That's kind of striking for me. How come? But that's not my question.
Yeah. But I can answer that.
You said you had very stringent rules to choose these species, and in particular that you chose at least 20 years, I think. Is that what you said? And I was wondering whether it didn't make more sense to use a number of generations rather than a number of years. And also, I think you kind of started answering that, but related to this, instead of measuring how the climate changes across, or the environment changes across, like annually or seasonally, maybe the scale should be, I don't know, like time to maturity or something related to the species biology rather than the calendar.
That's true. Yeah, that would be, I guess, pretty interesting. Like how long it should be based, it's not, I guess, I'm sure, actually, based on saying that if you want to detect a signal in the climatic conditions, you need at least more like 15 years of data. So that was the reason first you look at 20 years at least of data, wasn't related to the populations, but more about the variation. If we want to observe some variation and some signals, we went on that.
But that works if you're measuring this variation across years. If you decide to measure it across a certain scale that is related to the species, then that's not how you're going to choose the length of your data sets anymore.
Yeah, that's true. So we did also, like, in the way we choose the populations data, that was also not for insects. I agree that for that we didn't really interpret too much like the positive relationship, for instance, because we know that it's probably not a good scale. So what we use annual scales because most of the time in demography we use such time scale to estimate all the demographic parameters, even if it's a short-lived species, even if we know that we smoothed a bit what happened. We cannot explain everything. And ideally, I agree that it's what we should do, like to have like a proper relationship between what we try to measure and what we try to analyze. And for birds, I can answer what we use birds. So one of the selection criteria was not using migratory species because it's, again, harder to find which climatic conditions would impact the species. And then when we removed that, we drastically removed the availability, like the database that was available at least for the birds. And also because there were a lot of works on birds, we didn't like really spend too much time to try over datasets that were not published already, like contacting people, for instance. We didn't really do it. That was the reason at the beginning where birds were not included.
Any other questions on the chat? Yeah.
Last series of figures, you had generation time on the x-axis, and you saw signals for species with short generation time. And I was just wondering, on the same axis, you might have evolutionary responses. So do you think evolution could explain some of what you see, and it's not just ecological?
It's
Does
not
it
just
matter
what?
in any way your interpretations of signals you see?
Yeah, I really use often. So I use evolution for adaptation. So I interpret in terms of adaptation, where you expect that for the adaptation for different living species, explain that some evolve and adapt different, put it in that way. But there's probably over evolutionary processes that I've maybe ignored in my interpretation there. So if you have it, I'm very happy to hear.
Okay. Okay, again.
So in your different scenarios, using expectation from evolutionary theory that some traits are going to be more buffered than others, that made me think that you also having the scenarios about the sign of covariance between traits. And do you know if evolutionary theory predicts anything about which trait should covary? Like what would be the sign of covariation you expect in long-lived or short-lived species or something like that? Because
No, we don't really know.
because it seems like another case of buffering when you have one trait increasing and
It's
the other
exactly
one.
buffering. Like that's why like it reduced in the variance covariance components just because it buffered, like having like opposite relationship with the environmental variability, just buffered in a way. It's another way to buffer the response to variability. And it's something that we tried in another publication to see if we can detect different patterns along this fast slope continuum regarding the covariation. Could we expect more positive covariation for the long-lived species, and depending if it's on survival rates or fertility rates? And what we did, so based on empirical long-term time series, we just saw that most of the time it's positive. It seems to be positive relationship covariation, but it changed sometimes. Like there's something else that the fast slope continuum will explain the variation, because sometimes you have fluctuation where negative covariation can be observed, but it's not explained with the fast slope continuum, from what I know so far. And we don't have really over clues on it.
And so another question is that, so you have life history, like vital rates and climatic variables, but and you have also data sets that allow you to know what is the actual shape of this relationship between vital rates and climatic variables, to know if we are like more often convex or concave, because I guess in your simulation it was purely theoretical.
Yep.
So do we have enough data sets to do that?
That's the question. I tried to develop a project on birds actually, where we can just try to see if we see some nonlinearity relationship, so with very long-term and very detailed demographic parameters. And then it reduces a lot the possibilities, obviously. There's not so much data sets that allows such studies, but also, you know, what happens empirically is because it's also difficult to try and test.
De Sontoria, oui. You want to come up with us?
Minus.
Not a bird.
Okay, I noticed that we have a lot of young researchers in the room. So, well, not to say that too late, but feel free to ask questions. I mean, Christie is very kind, and so if you have any questions, no, yes, maybe. Anyway, she'll be set for next Friday, so feel free to pop up and have a chat with her. Any questions on the chat or no? Okay, so maybe we can call it today. Thank you very much again.
Thank you.